everyone, this is Manny here, and welcome to this lesson. Today we'll first study the properties of limits, and then learn how to apply these properties in order to compute these limits. In addition, we'll study some techniques to evaluate some special cases. Okay, so let's first study the properties of these limits. Now, the first property states that if you take the limit of a function with a constant in front of it, multiplying it, then you can basically pull the constant out and just focus on the main part of the limit. Now the next property says that if you take the limit of two functions that you're adding, then this is the same thing as adding the limits of the function separately. So you can take, if you're doing f of x plus g of x, then you can do the limit of f of x, g of x separately, then add or subtract them. Now, these two properties basically specify that limits are linear, so they specify linearity. Basically telling you that the limit is a linear operator, which satisfies these two cases, where you can pull the constant out as well as add or subtract them and apply the operations separately. Now the third case states that the limit of a constant is simply the constant itself. It doesn't matter what c is, and if you want to convince yourself of this, let's take a look at an example. Limit as x approaches 3 of 5. So right here, this is the equation y equals 5, or f of x equals 5. If you were to graph that, it's simply a horizontal line that goes through 5. If you take the limit as x approaches 3, no matter what side you come from, you'll still be able to approach that value 5 because it's a constant line. So therefore, the limit of a constant is simply the constant itself. Now the last property states that the limit of the function y equals x, or f of x equals x, is equal to the constant that we're interested in. So if we're doing x approaches c, then the answer is going to be c. So let's show why this is the case. So note that the function y equals x is simply a line that goes to the origin with a slope of 1. Now, if we were to take, say, for example, the limit as x approaches 3 from both sides, note that it's simply going to be the value 3, because it's at this point you're going to be approaching this point from that side, and then from the other side you're going to be approaching that. So that's going to be the value of 3. So therefore, the limit of as x approaches a constant for x is simply the constant that you're trying to evaluate. Okay, so now one of the interesting properties of limits is that you can apply it separately when you're taking a product of functions as well as a quotient of functions. And in addition, you can if you're taking a function raised to a power, you can just take the limit of the function itself and then raise it to that power. So if you're doing, for example, limit as x approaches 3 of x squared, then you can simply just take the limit as x approaches 3 of x, and then square it at the very end. Now remember, one of the properties is that if you're taking the limit of x, then it's the answer, the limit is simply whatever the constant of the value of interest is. So this is going to be 3. So you're going to get 3 squared, which equals 9. So let's apply these properties in the following example. Okay, so they tell us that the limit for f of x is 2, and the limit for g of x is 32. So remember that the property is that if you take a product of functions, you can take the limit of those functions separately and then take the product of those limits. But what is this? This is simply just 2. And this is 32. Right here. So therefore we can say this is 2 times 32, which is 64. Okay. Let's look at this one. This one is going to be the same kind of process. Remember that if you take a quotient, then you can take the limit of those separately. Just like this. Oops, that should be a g of x. And we'll turn back a slide so we can show you this property there. Okay, so now basically we can just say that's 2, and that is 32, and then we got to reduce this fraction, so you can divide by top and bottom by 2, so this becomes 1 over 16. So that was for part B. And let's look at part C. We're going to use a special property, the last property, which is the one where we have x approach c of f of x to the n power. We're going to use that property, and recall that that was equal to just a limit inside and then raise it to the power. Now remember, the fourth root, in this case of g of x, remember that the fourth root can be written as a fraction, exponent. So this can be written as a power n. So this can be written as g of x raised to the 1/4 power. Remember, the 1 is the power of here, which is an invisible 1 power, and the denominator is your index. So this becomes 1/4 power. So we can rewrite this as g of x to the 1/4 power, and then simply rewrite this here. Take the limit of just g of x and then raise the whole thing to the 1/4 power. Okay, or you can just say that this is the fourth root of the entire limit. You can do that. So we could just say the fourth root of, and then take the limit inside. So you can do that as well. Same process. And we know that the limit for g of x is 32. So we need to take the fourth root of 32. Okay, so let me just erase this real quick. Alright, so we need to take the fourth root of 32. And this is not a perfect fourth root, but remember, to simplify, we need to break it down. So let's break this down into 16 and 2, right? And note that the fourth root of 16 is 2, and you can't take the fourth root of 2 nicely anyways. So this is going to be 2. So you're left with 2 times the fourth root of 2. So you're left with 2 and fourth root of 2. And that would be your answer for C. Now let's take a look at D here. Remember the property that you can pull a constant out. And you can just take this and pull this out. So we're going to do that with the 3 here and the 2. We're going to pull those out. And then remember the sum property. So if you have a sum or a difference of functions, you can take the limits separately. So we're going to do that right here. So we're going to do limit as x approaches 0. And now we're going to pull the 3 out. So we're going to pull it here, pull it out. We have that, and then we're going to take minus the limit as x approaches 0 of g of x, and then just pull out the 2. We can pull that out here. And then we can make the substitution. So we said that this was 2. So we have here 3 times 2. Because remember, that's 2. And we have 2 times 32. Because remember, that is 32. So you're left with 6 minus 64, which is going to give you negative 58, if I did that math correctly. Okay, the next example, now we're actually taking the limits of functions themselves. So let's take a look at this one. So we're in the same way, we're going to take the limit as x approaches 3. Remember, these are all functions of x, right? These are all functions of x, sum and differences. So we can take the limit of each of these separately. Okay, so let's go ahead and take the limit of each of these separately. So, and then we can pull the 2 out. So we're going to pull out 2 out, minus, and then we're going to pull the 4 out of the 4x, so we won't have to deal with it yet. And then we're simply just going to do a limit of 5 for the last one. Okay, so how do we do this? Remember that the property, so you can take the limit as x approaches 3 of x, and then square the whole entire thing. Okay. And then remember with the property that the limit of x, it's just going to be the number, the value of interest. So this is going to be 3. So let's rewrite it here. So we got 2 times 3 squared minus 4 times the limit of x is going to be the value of interest. So it's going to be 3 plus, and then the limit of a constant is simply the constant itself. That's the very first property that we mentioned. So we have here 2 times 9 is 18, minus 12 plus 5. Then we have 6 plus 5, which is 11. Okay, so that's for part A. For part B, we're going to use the quotient property, right, where we take the limit of the numerator and denominator separately. Okay, so I'm going to take those separately. Here, let me rewrite this real quick. I'm just going to do it right here. So limit as x approaches negative 1/2. Now I'm going to split it. Remember, these are all functions of x, so I'll split it in the next step to show you. So we have here the numerator, and then we have the denominator. Okay. Then we can split the limit, right? So we can do the limit of x cubed, then the limit of 5, and then subtract them. And then the same thing for the denominator. And then remember, since it's x, we can do x cubed, and then we can take the limit for 5. And then remember, we can pull the 3 out when we have x. And again, the limit of 5. So the limit of 5 is going to be 5, remember. And this is going to be 5. This, remember, just the limit of x is just simply replaced with this number that you're interested in. So this is going to be negative 1/2. Okay, let me just write it over here. Okay, so this is going to be negative 1/2 cubed minus 5 divided by, this is going to be negative 1/2 as well, remember, just replace it. So 3 times negative 1/2, and then minus 5. Okay. Alright, so now we have negative 1/2 cubed, which is negative 1 squared is 1, or negative 1 cubed is negative 1. 2 cubed is 8. So we have negative 1/8 minus 5. And then 3 times negative 1/2. Remember, 3 is the same thing as 3 over 1, and then you multiply across. So we have 3 times negative 1 is negative 3. 1 times 2 is 2. And then you have that minus 5. Now remember, this is going to be over 1. This is going to be over 1. To combine fractions, we need a common denominator here. So we're going to multiply this by 8, since we need that to become an 8. So we have a common denominator. Whatever we do on bottom, we do on top, so we multiply that by 8. For this here, we need a common denominator of 2, so we're going to multiply this by 2, multiply this by 2. Alright, so we're left with negative 1/8 minus 5 times 8 is 40. And here 5 times 2 is 10, so we have 10 over 2. Okay, now we're okay to combine these fractions. So you're going to have the common denominator, and then you're going to be able to subtract these numerators. So negative 1 minus 40 is negative 41. And then you're going to have a common denominator for the bottom fraction. Negative 3 minus 10 is negative 13. Okay. Alright, if you want to divide these fractions, use KFC. That's what I use. Keep, flip, change. Okay, so we're going to keep the numerator here. We're going to flip the denominator, which the denominator is this whole thing, and this is the numerator. So we're going to flip the second fraction, basically, which becomes negative, or 2 over negative 13, and then change to multiplication. So we're going to multiply these. Alright, 2 goes into 8 4 times, and so we're left with negative 41 over negative 42, and 2 negatives make a positive here, so we have so we're left with 41 over 52. And let's do the second part here, or the third part here. So I'm going to skip some steps, just because it's the same principles here. So you can take the limit of these two separately, right, and then multiply them. Okay, so we're going to do the limit as x approaches 0 of 7x minus 2, but remember, we can just focus on 7x minus 2, and then take the raise it to the 6th power. And then we're going to do limit as x approaches 0. And remember, 2x minus 3, this is equal to 2x minus 3 to the 1/2 power, right? Because this is an invisible index of 2, and then an invisible power of 1, so it becomes 1/2 power. So we're going to focus on 2x minus 3, and then just raise it to the 1/2 power. Okay, so now we can simply do the limit of these separately. Okay, so we're going to do 7 limit of as x approaches 0. Okay, so 7 limit as x approaches 0, but we know from the property that that's just going to be 0. Limit of a constant is just going to be the constant itself. So we have that raised to the 6th power times limit. Remember, you can pull the 2 out, focus on the limit of x, but the limit of x is just going to be whatever this value is. So it's going to be 0, so you have 2 times 0. The limit of a constant is a constant itself. So we have here 0 minus 2 is negative 2, so negative 2 to the 6 is going to be 64. And then we have 0 minus 3 to the negative 1/2 power, or I'm sorry, to the positive 1/2 power, which in this case, this should be a plus, it should not be a minus. So sorry about that. You can't take the square root of a negative number, that should have been plus. So you get the square root of 3. So you have 64 square root of 3. Alright, recall that this is a piecewise function, and this is the exact same function that we went over last time in the previous lesson when we did one-sided limits. These are the exact same problems, copy-pasted. Now, we're going to learn how to do this analytically. So this is going to be easy, f of 1. So remember, f of 1, you're going to look for when x is equal to 1. The only condition I see where x is equal to 1 is right here. So therefore, I'm gonna use the function for that condition, which is this one. So that means when x is equal to 1, y is equal to 2. So this f of 1 is 2. Alright, so now if you want to do the one-sided limit, the limit as x approaches 1 from the left side of f of x, then we look at, remember, if you're doing x approaches 1 from the left side, that means you're looking at numbers that are smaller than 1, right? Numbers that are to the left of 1. You're approaching from the left side, and therefore you have these negative numbers, you have 0, and then you have fractions that are values that are smaller than 1. So you're basically are dealing with values that are less than 1. So you're looking for x being less than 1. So which condition has x being less than 1? It's going to be this one. This should say less than 1, but it says greater than 1, so I apologize. That's x less than 1. And so we're going to be looking at this condition, the first one. Okay, so that means we're doing the limit as x approaches 1 from the left side, and then the function that we're considering is 3x plus 4 now. Okay. Again, we're going to do the same process. We're going to pull 3 out, limit as x approaches 1, and limit as x approaches 1 for 4. It doesn't matter if it's a one-sided limit or not, it's still going to be the same rules. So this is still going to be 1 here. You're going to, the limit of x is going to be whatever the value of interest is here. So that's going to be 1. So you have 3 times 1. And the limit of a constant is a constant itself, so here you're left with 7. So your answer there is 7. And then we're going to do from the right side. So if you're approaching from the right side, remember that means this is 1, and then you're coming in from the right side, so you're coming in with numbers that are bigger than 1. So therefore you're looking for x is greater than 1. So the only condition that has x is greater than 1 is this condition here, where it says x is greater than or equal to 1, or in this case 1 is less than or equal to x. So we're focused on the 2, so we're doing the limit as x approaches 1 from the right side of 2, which in this case is just 2. F of 5, so you're looking at where x is equal to 5. The only condition where you have x is equal to 5 is here, where you have the bar. So when x is equal to 5, then you're going to plug in 5 minus 5 here, right? X minus 5, which is going to be 5 minus 5, which is 0. Now if you're doing the right-sided or the left-sided limit, then you're looking for values that are smaller than 5 because you're approaching from the left side. Therefore, x has to be less than 5. So you're looking for this condition here, x is less than 5. Sorry, that's x is less than 5, so therefore you're gonna be focused on this function here. So the limit as x approaches 5 from the left side of 2 is just simply 2. For the right-handed side, you're looking for values for x is greater than 5, which is this condition here. So you're gonna say limit as x approaches 5 of x minus 5. And then you split the limits and then subtract them. In this case, you're going to get limit of x is just going to be 5. Limit of 5 is going to be 5. So you have 5 minus 5 is 0. All right. So you may have noticed in the previous example, and I'll switch back to it right now. In this example, when we did the limit as x approaches 5 of f of x, and in this case from the right side it was x minus 5, and we just said that that was 0, right? But that's the same answer that you get if you just do f of 5, right? Which is 5 minus 5, which is 0. So does this always work? This is known as direct substitution, by the way, where you're directly substituting in for x into the function. Well, based on this example here with this piecewise function, this does not always work, because when we did the limit from the left-hand side, we got a value of 2. So it's not a simple plug-in chug. So if we just said, what is the limit as x approaches 5 of f of x, just in general, where f of x is this piecewise function, we're going to get does not exist because the one-sided limits do not agree. The limit from the right side is 0. The limit from the left side is 2. So this does not work in general. This only works for special types of functions. Functions that have certain properties. What property? Well, it has to be continuous. And we'll study this more in a later section where we study continuity. But basically, polynomials satisfy this criteria because polynomials are continuous everywhere, no matter what. So you can take the limit at any point, and you're going to be continuous, and therefore the one-sided limits are going to approach the same value, so the limit is always going to exist in that case. And it's basically the same thing as plugging in the x value into the function to get what the y value is. So this is a very useful tool, and instead of just breaking down the properties like we've been doing, you can just simply plug in the x value into the function if it's a polynomial. Now we can do this even if it's not a polynomial, but then we'll have to deal with certain special types of functions, and we're going to talk about those. Okay, so the procedure in general for computing the limits, just plug in the value of interest into the function. So if you're going to do, limit as x approaches c, or let's say 3 of f of x, try plugging in try doing f of 3. Okay, and then see what you get. Okay, so now if you plug in, so let's say you plug in f of 3 when you do the limit as x approaches 3. And let's say you get 0 over 0. This is known as an indeterminate form. Why is it indeterminate, you may ask? Well, the reason it's indeterminate is you have various cases that this may or may not belong to. Recall that if you divide by 0, you're going to get undefined, right? So if you have, say, 3 over 0, that's going to be undefined, right? So no matter what, if you divide by 0, that's going to give you an error, except when you get 0 over 0, which is what we're dealing with. Now, the case 2 is if you have a 0 in the numerator. If you have a 0 in the numerator, then the fraction is going to become 0, unless the denominator is also 0. And in the third case, and final case, is when both numbers are equal to each other, then you're going to get 1. So then we run into the dilemma, what case does 0 over 0 belong to? It could belong to the case where they're both 0, and therefore you get the value 1, or the case where you get 0 in the denominator, which is undefined, or 0 in the numerator, which is 0. So it can be any of these values, and it can also be a value that is not any of these cases. And this is why we call it indeterminate. And to be able to find the value of this depends on the function itself. And we'll be studying how to do those special cases. Okay, so if you get 0 over 0, then that means we have to simplify the function as much as possible, and we're going to be doing rationalizing and factoring polynomials. We're going to be doing those two later in this lesson, and then we'll learn other ways in another lesson. Now, once you rationalize or factor, then you cancel out any common factors, and then you plug in the value at the very end, and you're going to get a new value, which is not 0 over 0. You're going to get an actual number. Alright, so we're going to go ahead and plug in 1 into the function here. Alright, so we have negative 1 squared is 1, 1 plus 2, and then minus 3. So 1 plus 2 is 3, 3 minus 3 is 0. And we have 1, 1 minus 2 is negative 1, negative 1 plus 1 is 0. lo and behold, we have an indeterminate form, and we had to figure out how to deal with it. So basically, we had to simplify this function as much as we can. And since it's a polynomial, since the numerator and denominator are polynomials, a good bet is to try to factor them. So we're going to try to factor them here. Okay, so let's see, we're going to factor these two. These are both trinomials. So we're going to try to factor them. Factors of -3. Factors of -3 that add up to 2, which in this case are 1, -1, and +3. So therefore we have x minus 1, x plus 3. In this case we're dealing with factors of 1 that add up to -2, which in this case are -1 and -1. Okay, so we factored, we simplified. Now, remember one of the last steps was to try to cancel out any factors if you see them. So we have a common factor there that we can cancel. And then the final step is to go ahead and plug in the limit. So let me just rewrite it here. Alright, we're going to do direct substitution now. So 1 plus 3, 1 minus 1. Okay, so we have 4 over 0. Okay, so now we know that this is clearly going to be undefined, right? So we know that this does not exist. So we may not get an answer, but at least we know that the 0 over 0 belonged to one of those cases that we talked about. It doesn't have to belong to those cases. You could have easily gotten a number like 4, but in this case we got it does not exist. Okay, so that is going to be our answer. We're going to be doing the same process. Oops. Alright, so we're going to do 2 squared minus 7 times 2 plus 10 divided by 3 times 2 cubed minus 7 times 2 squared plus 2 times 2. Okay, so we have here 4 minus 14 plus 10 over 2 cubed is 8, 8 times 3 is 24, 2 squared is 4, 4 times 7 is 28, so we have minus 28, and then we have plus 4. Alright, so we have here negative 10 plus 10, negative 4 plus 4, which is clearly a 0 over 0 case. A big surprise there. So we're going to try to factor these because these are, again, polynomials. The top one is pretty easy. You find the factors of 10 to add up to negative 7, which in this case is going to be negative 5, negative 2. So we have x minus 5, x minus 2. And then for the bottom, we have to use AC method. You could use AC method, guessing method, or you can do a little table. Well, first of all, let's factor out the x. So we get x times 3x squared minus 7x plus 2. Then we can do the AC method or any other method you choose, but I'm going to multiply 3 and 2, which gives me 6. Okay, so then we're going to multiply 3 and 2, so we're going to do the AC method here. 3 and 2 is 6, and then we're going to do the factors of 6 that add up to negative 7, and those are negative 6 and negative 1. Then we take this polynomial and split the middle term into these two terms. Negative 6x minus 1x, or just minus x, plus 2. Then we're going to factor by grouping. So we're going to put these into two groups here. And then we're going to pull out from each group. The greatest common factor for these two is 3x. 3x times x gives me 3x squared. Then we have x minus 2. Then from here, notice we can plug out a negative, take out a negative 1. So if we take out a negative 1, we're left with x minus 2. Alright, and then your factors are going to be x minus 2. Notice that these match. So one of your factors is x minus 2, and your other factor is going to be 3x minus 1. Okay, so then this turns into x minus 2 times 3x minus 1. Okay, notice that the x minus 2's cancel, and leaving us with this, and then we can go ahead and just plug in the 2 for every x that we see. So we're going to have 2 minus 5 over 2 times 3 times 2 minus 1. 6 minus 1 is 5. 5 times 2 is 10. 2 minus 5 is negative 3. So finally, that is your limit. So in this case, we got a number. Now in this case, we're going to... This top part is a polynomial. We can plug it in. I mean, we can plug it into anything. So when we're going to see if we get 0 over 0, which by now you should know that we will, but just for the sake of the process. So we have 2 squared is 4. 4 minus 2 is 2. 2 minus 2 is 0. So a lot of 2's here. We have 2 plus 2 is 4. Square root of 4 is 2. 2 minus 2 is 0. So we get 0 over 0. Yay. So now, that means we have to figure out what to do. This top part is a polynomial, so we can probably factor that. Now this part is a radical. So that means we're probably going to have to rationalize the denominator here. So we're going to try to rationalize that. Remember, to rationalize this, you multiply by the conjugate. Now the conjugate is the same exact form. It's going to be 2 and square root of t plus 2, but the middle sign is going to be opposite. Okay, so in this case it's going to be 2 plus square root of t plus 2. That's going to be the conjugate. So we're going to multiply. Well, before we multiply that, let's factor the numerator. So the numerator, factors of negative 2, that add up to negative 1, which in this case is negative 2 and positive 1. So we have t minus 2 and t plus 1. Now we're going to try to multiply by the conjugate here, top and bottom. Okay, so remember, this is the form a minus b times a plus b. Remember that a plus b times a minus b is simply a squared minus b squared. So this is going to save us some work here on the bottom. So on the bottom, we have 2 squared minus, and this squared. But remember that the square root of t plus 2 squared is simply t plus 2. So that leaves us with 2 squared, which is 4, minus parentheses t plus 2. And don't worry about multiplying this top part. You don't have to worry about that. You can simply leave it as a set of factors. We're going to simplify the bottom, however. So you're going to get 4 minus t. So remember, you're going to distribute the minus here. So you have 4 minus t, and then you're going to have a negative 2. So this becomes 4 minus t minus 2. And 4 minus 2 is 2. So that leaves you with 2 minus t. So I'm going to erase that here. So that's going to leave you with 2 minus t. This is pretty close to t minus 2, note. How do we make it into t minus 2? Well, we'll just factor out a negative. So let's factor out a negative from this. And that changes this into minus, and that changes that to plus. Which notice that by the commutative property, this is the same thing as t minus 2, right? Negative 2 plus t is the same thing as t minus 2. So then now we can proceed to cancel. Just keep in mind that the negative sign is there. Okay? So if we want, we can take that negative sign and put it out here, because this becomes 1 now because it canceled. Then you're going to go ahead and plug in the limit. So you're going to have t plus 1, which is 3. 2 times 2 is 4. 2 plus 2 is 4. Square root of 4 is 2. So you have 4 times square root of 4, which is square root of 4 is 2. 2 times 4 is 8. 8 times 3 is 24. And then don't forget the minus sign. So we have negative 24. Okay, and that's the answer for part C. Okay, so the next example, we're going to calculate the value of this following limit, and this limit has an absolute value in it. Okay, so as with all the limits so far, we've just been able to just plug in the value of interest. So we're going to plug in 2. And if you do it, you're going to get absolute value of 0 divided by 0, which of course is 0 over 0. Okay. So what are we going to do? Well, we're going to have to factor, right? Find some way to simplify this. Okay, so let's go ahead and factor 3 from this top. And recall, to factor this, you need the factors of negative 4 that add up to 0, which because the middle term here is 0. In this case, that would give you negative 2 and 2. So your factors are x minus 2, x plus 2. All right. Next, just notice that you have a product here, and for absolute values, you can take the product. You can take the absolute value of each of these individually. So you can rewrite this as absolute value of 3 times absolute value of x minus 2 over x minus 2, x plus 2. Okay, now we gotta be extra careful when we're dealing with absolute values. Okay, because absolute values are actually can be considered as piecewise functions, which means that we need to evaluate the one-sided limits for this function. And I'm going to explain that right now, because we need to know how we can define an absolute value. So let's try. Let's define what the absolute value of x is in terms of piecewise functions. Okay, so absolute value of x can be considered to be x if x is greater than or equal to 0, or it can be negative x if x is less than 0. Okay, this is very important. It's considered a piecewise function. So for example, if you had absolute value of negative 3, well, negative 3 is less than 0. So then if you go on this piecewise function, it would be negative 3, which is 3. Okay, so this is how you can consider a piecewise absolute value as a piecewise function. Now, how do we do x minus 2? So I'm going to show you in a separate board here. Okay, so absolute value x minus 2. We can consider that to be x minus 2 if x minus 2 is greater than or equal to 0. Or we can consider that to be the opposite of x minus 2 when x minus 2 is less than 0. Let's simplify this a bit further. So we have x minus 2 when x is greater than 2. So if you move the 2 over here, you're going to get greater than 2 or equal to 2. And then same, you're going to get x is less than 2 here. And then you're going to distribute the minus. So you're going to get negative x plus 2. And remember that negative x plus 2 is the same thing as 2 minus x, right? So, so it's the same thing as 2 minus x, but we'll just leave it as negative x minus 2. We just so that if you wanted to simplify, you can write that. Okay, so this is the piecewise function. So then if you wanted to do the limit here, so if you wanted to do, let's go back. So if you wanted to do this limit, then you just have to be careful, and you have to be able to do the one-sided limits for this function. So let's do the one-sided limits. So if you evaluate it from the left side, that means you're looking for x values that are less than 2, right? So you're going to go to this piecewise function here, and you're looking at values less than 2. So that means it's going to be the opposite of x minus 2. So we need to replace this with this, and that's very important here. So we're going to replace it now. It's going to be an absolute value of 3 is just 3. So we're going to do 3, and we're going to put the negative out here because x minus 2 is going to be the opposite. So 3 times negative x minus 2 is negative 3 right here. See, now we can release the absolute value because we used the definition of it, and then we can proceed to cancel out. So do not proceed to cancel this out unless you have done this step. Okay, so now you have negative 3 over x plus 2, and now you can proceed to plug in 2. So you're going to get negative 3 over 2 plus 2, which is negative 3/4. Okay, so that is from the left side. Now what is it for the right side? Let me just write it over here. So if you do it from the right side, then recall, let's go to the other board, let's recall that it's going to be the original function if it's greater than or equal to 2, which is the case because we're coming in from the right side. So we're just going to simply replace, we can simply release the absolute value bars and write it as x minus 2. So these cancel. You're left with 3 over x plus 2, and now you can proceed to do a direct substitution, which leaves you with 3/4. So this means that the general limit, or the overall limit, right, of, I'm just going to call this f of x, does not exist because the one-sided limits don't exist. So be very careful. Do not cancel this out because you're just ignoring the property of the absolute value. Remember, it's more complicated than it seems. Okay, so in this example, we have does not exist. Okay, so let's summarize what we've been doing. We talked about the properties of limits, and we use these properties in order to evaluate the limits, right? So we've done a couple examples with properties. We've also used these properties in order to determine that we can do a direct substitution with these limits as long as the functions have the property, and we said that the specific property that they need to have is continuity. And polynomials are continuous everywhere, and therefore we can do a direct substitution with no consequences whatsoever. We'll get the right answer. However, if you have a function that is not a polynomial, or a function that is not continuous, doesn't have this property, such as piecewise functions, certain types of piecewise functions, you can do a direct substitution, but you have to consider which side you're approaching from, or if you get a 0 over 0, right, an indeterminate form, then you have to simplify the function in order to be able to cancel out any factors, and then you can do a direct substitution. And then we also just did an example on absolute value limits. And we talked about the properties of absolute values. Remember that they're piecewise functions, so you have to be very cautious when dealing with a limit that has absolute value in it. Okay, that concludes this lesson. I hope you understood the content, and just keep practicing the material and you'll understand it in no time.